Good evening one and all. Today is 16th of June 2023. We are in module 5 of Professional Electrive 3 Electric and Hybrid Vehicles. We are in the last topic, that is hybrid drivetrain design. In that we are actually seeing the parallel hybrid electric drivetrain design. And two topics that we are going to see today is the control strategies for parallel hybrid electric drivetrain design. In that case, two different types of controls we are going to see. One is called as max state of charge control, that is max SOC control. Next is engine on off thermostat based control. Both these topics can be found in our textbook of Ehsani, module number 9, starting from page number 255. First we are going to see or have a very brief recap of parallel hybrid electric drivetrain. In this case we are finding there is a primary power source, which is the engine. This is giving mechanical power output which is going to the transmission. There is a secondary power source or peak power source, which is the battery. This is giving its output to the motor by a controlled motor controller, and motor output is also mechanical. So primary source mechanical output after clutch, transmission, and secondary source mechanical output after the motor, they are getting combined in a torque coupler. So there are two types of coupling. I said one is torque coupling, one is speed coupling, but in this case configuration of parallel hybrid is given by means of a torque coupler. Torque coupler is giving the output to the differential. From there mechanical power is given to the wheels and the vehicle is driven. Now vehicle controller is a primary controller. It is actually having various kind of inputs from different positions. So first input is coming from the driver, the torque or the acceleration, that is the first input. Second input is brake, and third input is direction. So all their operation commands, it is coming to the vehicle controller. Now vehicle controller is connected to other controllers, which is called as a engine controller. You can find here the vehicle controller is connected to the engine controller. It is connected to the electric motor controller, which is here, and the vehicle controller is connected to mechanical brake controller. So vehicle controller is a master controller, others are called as a slave controller. So there are different inputs coming from different parts of the vehicle to the vehicle controller. One is the speed. There is a speed sensing. From the axle it is coming to the vehicle controller. From the engine also there are different types of speed sensing of the crankshaft, that comes to the vehicle controller. Whatever is the status of the battery, how much is the charge, voltage, current, temperature, all the inputs come from PPS source to the vehicle controller. All these different brake, whatever are the brakes status and other thing inside the fluid chamber, brake fluid chamber, what is the status of the fluid and pressure, they also come to the vehicle controller. So depending on the operation command and mixing them with different present status sensed input of the vehicle controller decides what is going to be the next control strategy, and that is actually sent to the engine controller, which controls the primary power source engine, which controls the secondary power source output, that is the peak power source and motor, and output of the motor and output of the engine are combined to generate the final control element, which is nothing but torque. Now in this case you are finding that there are three types of signals. One is a mechanical power, so which is found at the output of the motor, output of the engine, output of transmission. So these are double line things. These are mechanical output power, mechanical connections. Dark lines are electrical connections, which may be found at the output of peak power source, motor controller, and input of the motor. And there are a lot of signals which are picked up by sensors, like this vehicle speed sensor, like this operation command, like this throttle position. Throttle position sensor is nothing but which is controlling the output of the engine. So if engine wants to increase its output, in that case the throttle valve through which the fuel goes inside the engine will be opened, and the engine will be producing higher mechanical force. So this throttle position sensor is also coming to the vehicle controller. So all this command inputs and sensed inputs, all those things are put together, and vehicle controller decides what is going to be the next engine control strategy, or next motor control strategy, or next brake control strategy. All these things are decided by the vehicle controller. So you are finding at the top there is a mechanical brake controller. It is connected to the right side wheel, it is connected to the left side wheel, all are rear wheels. Similarly in the front wheels also they are connected. So all these things together is given to the vehicle controller, and vehicle controller decides as per the sensed inputs to it. So this is the kind of rough sketch or rough block schematic of electric hybrid parallel drivetrain. Now all the power nomenclature that we have used, you are finding beside engine we have written PE, and beside motor we have written PM. So PM is the motor power, P is the engine power, PL is actually the load torque which is being requested from this vehicle controller by the vehicle. So whatever is the vehicle or whatever is the driver, whoever is the driver, they are asking this PL load power from the vehicle controller. Now this PL is of two type. If the vehicle is in traction, this will be the traction power. If the vehicle is going into the brake mode, at that time PL will be the brake power that has to be generated by the vehicle. Now you are finding there is battery charging. It is called as battery, whatever is the energy stored in the battery, it is called as PPS, and PMC is the motor charging. Okay, and there are two brake powers. One is called as mechanical brake power given by PMF, and there is the electrical brake power or motor brake power which is given by PMB. So this PPS is producing the motor brake as well as motor traction. Both power are coming from the peak power source. So the engine supplies its power to meet the base load demand. What is the base load? It is nothing but the operating at a constant speed on a flat and mild road, flat and mild grade road, or the average of the load of a stop and go driving pattern. So base load is generally supplied by the engine. It can be a flat road, it can be a mild grade, that means very small 2-5 degree grade, or it can be stop and go driving pattern inside the city, or this whole drivetrain, that means primary and secondary source together, they will be supplying the bumper power to meet the peak load demand. What is meant by the bumper power? That is power from the peak power source, that is power from the PPS, that is the extra power. This is called as a bumper source, which is actually given in a very specific time, which is not throughout present in the drive operation. Throughout present in the drive operation is the engine power, and a bumper power is required only when the vehicle is this is the instantaneous power when the vehicle is going up the hill or accelerating very fast at that time. So you are finding that this engine supplies all the basic load and the electric motor supplies the bumper power to meet the peak load demand. So generally the base load is supplied by the engine, and whenever the too much of power demand is there, at the time engine power is mixed with the bumper power from the PPS, and then the total PL is satisfied by the vehicle. And there are mainly 4 controllers you are finding, that is vehicle controller, engine controller, motor controller, and mechanical brake controller. These are the basics of maximum SOC of PPS control strategy. It is saying that when the vehicle is operating in a stop and go driving pattern within the city, PPS must deliver its power to the drivetrain frequently, and in this process actually the PPS gets discharged. So whenever you are driving through the city, at that time more than engine, the battery source actually it delivers the power to the final drive element, because stop and go kind of driving characteristic is better suited to the battery than the engine, because starting and stopping of the engine itself is a very big job, and engine is having much more inertia than the battery. So whenever we are finding this stop and go kind of driving pattern within the city, it is better we use the electric source or PPS source or battery. But in this process the PPS gets discharged. So the job of engine becomes in next time, that is it has to supply the load to the vehicle. That means it has to supply the PL or load power demand, it has to satisfy. At the same time it has to recharge the PPS source also. So here maintaining a high SOC in the PPS is necessary to ensure that PPS can deliver sufficient power to the drivetrain to support the vehicle's frequent acceleration. So there are two things coming. One is PPS is getting discharged when the car is being taken through the city, and when the PPS gets discharged, then the responsibility comes on the primary source or engine to recharge the PPS, because whenever there comes the next high demand from PPS, PPS should be prepared to supply the bumper power to the vehicle. Okay, so maintaining a high SOC in the PPS is necessary to ensure that the PPS can deliver sufficient power to the drivetrain to support the vehicle's frequent acceleration. Basic rule of this control strategy, that is maximum SOC of PPS, is that using the engine as a primary power source as much as possible. So most of the time we will be keeping the engine as the main power source as much as possible, and PPS whenever the engine has excess power over the required for propulsion. That means as long as the PL, as long as PL is less than PE, we are going to supply the power from PE itself. P is the engine power. But whenever the PL exceeds PE, at that time the PMC or battery power or PPS power, that will be utilized. So most of the time engine will be giving out the power to run the vehicle, and whenever the engine has excess power required for propulsion, that will actually charge the PPS. So there are two things. One is excess power when required from the battery sources or from the vehicle. At that time engine and PPS together will supply the excess power. And secondly, whenever less power is required from the vehicle, at that time engine will do two things. It will drive the vehicle as well as it will charge the PPS at the same time. So this is mainly the basic behind maximum SOC of PPS strategy. So what we are going to find is in this control strategy there will be four traction cases. So first traction will be engine alone control. That means only the engine is providing the load power. That means load power is quite small. Second case is electric motor alone. So this is a very special case, you have not seen this. That means when the electric motor only is giving the power to the load. So in this case we will see a very specific case at the starting of the whole parallel hybrid electric drivetrain, where we will see that motor alone will supply the traction power. So this is a new case for us. We will see that engine alone we have discussed in previous series hybrid electric drivetrain as well, but motor alone is a very specific case here in case of parallel hybrid electric drivetrain. We will see that. And when total power required by the vehicle is quite high, okay, greater than the engine alone traction, at that time maximum power curves for hybrid traction is used. So in that case hybrid mode is used. In this case engine and PPS together they supply the load demand. Fourth case is regenerative braking. In that case vehicle is going downward, so in that case the drivetrain will generate power in the reverse direction. Power from the output will come and it will charge the PPS battery. So apart from this traction there are two cases of braking. So in the braking we will be finding there are two types of braking. One is only electrical braking, which is supplied by the PPS source, and another is hybrid braking. So during hybrid braking electric source and mechanical braking together they will be giving the output brake power. Power demands in different conditions are also plotted, represented by 4 points A, B, C, D, as we had found in case of previous series hybrid electric. But in the previous case there were 4 modes. Okay, so this is the graph you have to produce during the exam. In this case you are finding these are the 6 modes. Okay, and there are 4 points A, B. B is having again 2 points. One is capital B, one is small b. So A, B, C, D. Okay, so these 4 points are not exactly mapped to this 6 operating modes, though their name are same. These operating modes are also given by capital A, B, C, D, E, F, but these points are actually given by A, B, C, D. So I will say that mode A, B, C, D, E, F and point A, B, C, D. So mode and point, they are not mapped 1:1. I'll give a very small example here. But before going for the modes and points, let us see what are the variable parameters. We are finding line 2. So this is line 2, which is maximum power with electric alone traction. So it is starting from 0, going up, getting saturated. So when the electric motor is acting alone, at that time this is the power curve given by 2. What is number 3? Engine power on optimum operating line. That means this is a maximum engine power that can be produced by the primary power source. That is line 3. And if you are adding 2 and 3, we are getting 1. What is 1? 1 is the maximum power in hybrid mode. So 2 is the PPS maximum power, 3 is the engine maximum power, 2 plus 3 is the maximum power given by the vehicle drivetrain together, and this is called as a hybrid power mode. Okay, now see this point A. What is point A? In point A we are actually asking for too much power. Too much power from the vehicle is required, so you are finding PL. So load power is very high. Load power has crossed the engine power, that is this thing. Load power has crossed the electric motor power. Okay, so in this case A has to be a hybrid case. In this case we have to add this 2 and 3, that is we have to add the power from the engine and motor, then only we can supply this point A. So actually A is actually a hybrid mode of driving, but in this case A is not hybrid mode. So this is point, so this A point is not matching to the mode A. Okay, rather A point is matched with hybrid propelling mode, that is B. So point A, whatever we are finding, which is a hybrid mode, you have understood it. This is not mode A, this is actually mode B. So don't try to map this A, B, C, D with this modes A, B, C, D, E, F. And moreover, there are only 4 points A, B, C, D, and here you are finding there are 6 modes. Okay, so A, B, C, D cannot be mapped to A, B, C, D, E, F. So these points are different, modes are different. So I told you all these 3 lines. So line number 2 is electric maximum power, line number 3 is motor maximum power, sorry, engine maximum power. So 2 is motor or PPS maximum power, 3 is engine maximum power. If you add them, you are getting hybrid maximum power, that is line 1, which is called as maximum power in hybrid mode. Then 4 is engine partial power. So partial load, that means when the engine is supplying only the load, it is not charging the battery. Okay, so this is the difference between point capital B and small b. In capital B is actually, this is the minimum power generated by the engine, which is only supplying to the load, because in this case PPS is fully charged. And what is small b? Small b is engine is producing power PE, which is satisfying the load of the motor PL, and which is generating some charging power. So PM here, in this case you are finding PM is the motor output power, but PMC is the motor charging power. So here the motor is giving out power, and motor is taking the power from battery and giving out to the output vehicle, that is it is supplying to the PL. But in this case point B, which is the difference between PMC. Okay, so PMC is creating the difference between small b and capital B. You are finding that small b plus PMC is equal to, sorry, capital B plus PMC is equal to small b. So small b is the point on the optimal, that means maximum output power of the engine, and capital B is actually the unloaded or partially loaded output power from the engine, like that. Okay, so we are going to see all the 6 cases, and you should know these parameters. PL is the load power demand by the drive elements, P is the engine power, PM is the motor traction power, that means this is the motor power giving at the output. PMB is the motor braking power. So below this line, central line at the center, okay, so this x-axis, what we called, this is actually 0. Below this 0, whatever we are finding, this is actually the braking mode, and above this 0 base, whatever we are finding, it is called as traction. So in the exam, if I ask you A, B, C, D, that means all the traction modes, you need not to draw this below part. Okay, if I ask you only the EF, that is the braking part, at that time you need not to draw the ABCD part. If I ask you explain all the modes, operating modes, then only you have to draw all this A, B, C, D, E, F, right? So you should know actually what is what, and it will, if you go smart, it will save some of your time during the exam. So depending on whatever cases are asked to you, you have to drive the cases. Maybe I'll ask hybrid braking, so in that case you have to only show D. I did not ask you about electrical braking, so no need to draw point C at that time. Only the hybrid braking, point D, you have to draw. So P is the engine power, PM is the motor traction power, PMB is the motor braking power, PMC is the PPS charging power, which you are finding difference between capital B and small b. In this case the motor is charging and PM is actually the discharging, that means motor is giving power to the load. PMF is the mechanical brake power, you are finding here, because in D, whatever is the brake power asked by the vehicle, it is too much. Okay, so PMB is nothing but the brake power given by the motor, but demanded brake power is D, which is very high, which has crossed the PMB max limit. So who is going to supply the extra braking power? It will be mechanical brake. So PMB is the electrical brake, PMF is the mechanical brake. Together they are producing the total brake power, which is called as a PL, right? And there is another thing which is called as a line 5. Line 5 is the maximum generative power of the electrical motor. That means this is the regenerative braking maximum power. You are finding this line 2 and line 5, they are actually equal and opposite. So whenever the motor is running in the forward direction, it is generating curve 2. Same motor from the same PPS source acting in a different direction or rotating in a different reverse direction, it is going to generate the line which is called as a 5. Okay, there is something called as a VEB. This is a very important thing, and VEB I will explain while I am explaining the first mode of operation, which is called as A. What is A? You are finding here A is motor alone propelling mode. So this is something very new for you, so be careful. So I am telling you VEB. What is VEB? So VEB says that vehicle speed corresponding to engine minimum RPM. That is what is called as a VEB. What is meant by that? It meant by that between 0 to VEB engine is not started. Let's say VEB is equal to 20 km per hour. Let's assume. So between 0 to 20 km per hour engine did not start because engine is starting from VEB. So how did the vehicle increase its speed from 0 to 20? It was all done by motor alone. So here for this region you are finding whatever I am showing, just see the cursor. So from 0 to VEB and project VEB directly upward in this triangle, okay, in this triangular position, total power is being supplied to the load by the motor alone. That means PPS is getting discharged at the starting of the vehicle start only. So whenever the vehicle is started, at that time always this parallel hybrid drivetrain, whenever it is started, it will be started with electrical, because engine does not start till 20 km per hour. So this is a special region which is called as VEB, which is called as vehicle speed corresponding to the engine minimum RPM. Let us see how it goes. So motor alone propelling mode, it is said that if the vehicle speed is less than the preset value VEB, so vehicle speed is here somewhere around 5 or 10 kilometers, VEB is 20 kilometers. So VEB is the lowest vehicle speed for high fuel consumption and high emission. So VEB is the lowest speed for engine. This is not the lowest speed for vehicle. Lowest speed for vehicle is 0. But VEB is the lowest speed for vehicle. So if the vehicle speed is less than a preset value VEB, preset for engine, which is the lowest vehicle speed by the engine, the vehicle operates with high fuel consumption and high emission. So even at 5 km per hour, 10 km per hour, you could start the engine. But in that case, engine will consume very heavy fuel and it will be giving very high emission, which will create a huge amount of pollution. And it will be operating with very less efficiency. In that case, lot of unburned fuel will be exhausted in the air. So before this VEB 20 km per hour speed, we are not using engine to start the vehicle. So in that case, below this VEB vehicle speed, electrical motor alone propels the vehicle. So below this 20 km per hour, PL is supplied by PPS or PM. Meanwhile, the engine is shut down. That means between 0 to VEB, engine is shut down or it idles. Idles means it is off, but it is preparing to getting on with the clutch open. Okay, so we have seen in the characteristic block diagram that there is a clutch. Okay, so if the clutch is open, that means in this case only the engine will be running or it will be idling, but no power will be given to the transmission. So that is what is said, that whenever the actual vehicle power vehicle speed is less than VEB, at that time electric motor alone propels the vehicle. Meanwhile, the engine is shut down or idles with the clutch open. Engine power, electric traction power and PPS discharge power can be given as PE is equal to 0 because the clutch is open, engine is not contributing any power to the drivetrain. PM is equal to PL, so load power is already taken from the always being taken from the motor, and PPSD is equal to PM by eta M. So whatever is the efficiency of the secondary drivetrain, PPS is the secondary drivetrain. So PPS is equal to PM divided by eta M. Okay. So P is the engine power, which is equal to 0 because clutch is open. PL is the propelling power demanded by the driver. PM is the power output of the electric motor. So electric motor output is coming from PPSD. Eta M is the efficiency of the secondary drivetrain, and you are finding that if 100 watt is required by the motor to drive the load, suppose if load is PL is equal to 100 watts and PM is equal to 100 watts because PL is equal to PM, with the drive efficiency of the 0.9, PPS has to produce actually 111 watts. So if the PPS is producing 111 watts, then only 100 watts will come to the motor and the motor will be able to supply the load with 100 watts. So this is happening as long as the speed of the vehicle is not picking up to VEB, which we have assumed let it be 20 km per hour. This is a very special case which you have not seen previously. This is motor alone propelling mode. Let us now see what is the next type of mode or next mode for parallel hybrid electric drivetrain. It is called as a hybrid propelling mode. So you are finding this point A. This point A is far above the line 2 or line 3. What is line 2? Line 2 is the maximum output power from the electric motor alone. Line 3 is the maximum or optimal efficiency or optimal output from the engine alone. But whatever the point A position is, so this is not mode A, this is mode B, but it is point A. So mode B is depicted by point A. So you are finding too much of load power is asked, so PL is very high. Okay, and actually PL is given by PE, that is the engine power at point A, and PM. So PM is nothing but the PPS is discharging, and PPS is discharging through motor. That's why this PM is actually PPS. PPS is coming from the PPS source, PE is coming from the engine. So PE plus PM is equal to PL. You are finding almost engine and motor contributing 50% each. So this is that hybrid traction mode, and this is the main mode for which this drivetrain is designed. So you can very easily see that 2 and 3 is less than point A, hence 2 and 3 together they are actually supplying this PL. And you are finding this A is actually below this graph 1. What is graph 1? Graph 1 is actually the addition of 2 and 3. So this is the best example of hybrid mode. Let us see what is written in this slide. So here the propelling power demanded by the driver, that means PL, is given by PL, which is represented by point A in this figure. As the demanded power is greater than the individual power, that is PM and PE, both the engine and electric motor will drive together, deliver power together to satisfy the PL requirements or the drivetrain requirement. In this case, the engine operation is set at its operation line point A. So you are finding there are two graphs 3 and 4. So out of these two, 3 will be used here, because in this case engine is to be run in an optimum case, because maybe maximum power we might require from engine. So that's why the line 3 is taken in this case. So this projection of a small a point is taken from line 3, not from line 4. Okay, so this A projection is taken here and this much below. So from here to this projection to this ground line 0, this is actually the engine power. So in this case, the engine operation is set to its optimum operation by the controlling the engine throttle. That means we are actually controlling the throttle valve which takes the fuel inside the engine. So that control by the engine controller controlling actually the power of the engine, so PE. So throttle control is actually producing this line 3 output. So this optimum output from the engine is actually controlled by the throttle valve. So in this case, the engine operation is set at its optimum operation line point A by controlling the engine throttle to produce power PE. Remaining power, so PE is given by the engine, PM power, because PM plus P is equal to PL. PM power is the remaining power which is actually supplied by the PPS, or which is called as a PM. So in this case, PL is equal to PE plus PM, or PM is equal to PL minus PE. So this is what you are finding. This PE, if you take in the left side, equation will become PL is equal to PM plus PE. But mainly we are more interested in designing the parameters of the PPS source. So that's why PM is equal to PPS. So PM is equal to PL minus PE. Now PPS is equal to PM divided by eta M. We have found that secondary drivetrain is having an efficiency of eta M. That means if it is eta M is 90%, if PPS is 111, at that time we can supply the load power PM is equal to PL is equal to 100. So first we have to see how much is the PM required in this case. Depending on that, we have to divide that by 0.9. That will be actually the PPS power which is extracted from the battery. So this is a hybrid propelling mode which is given by point A. We have seen the same kind of thing in case of series hybrid electric drivetrain also. So there is no difficulty in this to understand. We will go for mode C. What is mode C? It is called as a PPS charge mode. Now you are finding this graph 3 and graph 4. What are the names? Graph 3 is engine power on its optimum operating line. Graph 4 is engine power with partial load. Difference between graph 3 and graph 4 is both are engine power, but 3 is when engine is doing two work. What are the two work? It is supplying the load as well as it is charging the PPS or battery. So this is small point B. Okay, small point B is on the line 3. Line 3 is the optimum or maximum engine power output. It is doing two things. It is generating the PL, which is called as a load. So you can find here this is PE. Okay, so this is the total engine power, and engine power is doing two things. One is PL, that means whatever is the load power asked by the vehicle, that is supplied by the engine itself. And secondly, PMC. So PM stands for motor power or PPS power, and this is MC stands for charging. So in this case, whatever power is produced by the engine, this is doing two things. I am talking about graph 3 or point small b. It is doing two things. It is supplying the load as well as it is supplying the power from the PPS to get charged. So this is actually this mode, that is mode number C. So when the demanded propelling power PL, which is represented by capital B. So capital B is only the demanded power by the vehicle. This is point B. But the engine is producing, PE is producing actually more than that. Engine is producing small b, and you are finding small b is higher than capital B. Question can be asked, if vehicle is requiring power PL, why the engine is producing a higher power, that is PL plus PMC? Because engine knows that in previous case A or previous mode B, it was hybrid driving, or A also in mode A, where motor was driving the vehicle in less than VEB speed. So at the starting as well as in hybrid driving, we have lost quite a lot of power from the PPS. So in the first two modes, that is A and B, lot of power wasted from the PPS source. Now that has to be compensated. So that's why when the load on the vehicle is less, at the time engine on its own, based on the algorithm, it starts putting more amount of charge back to the PPS. Because again, when next time hybrid vehicle operation comes, in that case this PPS has to supply more power. So that's why knowingly the engine generates more power. So when the demanded propelling power PL, which represents by point B in the figure, is less than the power that the engine can produce while operating on its optimum operation line. So you are finding that for this capital point B, actual demanded power is on line 4, but engine is working with line 3, which is generating a lot more power. So this is giving the same thing. Demanded propelling power PL, which is represented by point capital B in the figure, is less than the power that the engine can produce while operating on its optimum operation line. And the SOC of the PPS is also below the top line. So another sensing you have to do, you have to sense when the PL, that is capital B, this much power is asked by the engine. At this time, you have to also ensure that PPS is not saturated. That means PPS has not reached this level 2. And PPS cannot reach the level 2 because in the first two modes, A and B, both the cases PPS has discharged heavily. That's why PPS SOC is very less. So when it is the vehicle engine is at point small b, and when SOC of the PPS is lot less, then this mode, that is mode number C, it is going to do, it is coming to act. So SOC of the PPS is below the top line, then the engine is operated on its optimum operating line, that is line number 3, point B, and it is going to produce power PE, and you are finding PE is greater than PL. In this case, what you will be finding is the electric motor is controlled by the controller. That means there is a motor controller which will be controlling the electric motor to function as a generator. And to function as a generator, it has to take the power from the output side, and it has to take the power inside the battery. Who is giving that power? That power is coming from the energy source number 1, that is engine. So this PMC is then giving the power to the motor controller. Motor controller is taking the power back to the battery. So in this case, the electric motor is controlled by its controller to function as a generator powered by the remaining power of the engine. Remaining power of the engine means P is quite high. It is generating two power, PL and PMC. PL is going for driving the vehicle. PMC is going to charge the battery. So the input power to the electric motor and the PPS charge power are, we are finding PM is equal to, so this PM is equal to PE minus PL. So PE is the whole power minus PL. Okay, so PE minus PL, if we do, that much is the remaining power multiplied with the efficiency of the drivetrain. So whatever is the efficiency of the drivetrain from the engine to the battery, so there is no direct path, there is an indirect path. So from engine to the clutch, to the coupler, and from the coupler back to the motor controller, and from there motor, and then to the battery. So all this efficiencies together, we are calling it as a eta TEM. So remaining power multiplied by eta efficiency, combined efficiency, that much energy will go to PM, and the PM will keep on getting charged. That means PPS is going to get charged with some efficiency which is given by eta. So PPS is equal to PMC is equal to PM into eta M. So that is PM is nothing but P minus PL, where eta TEM is the transmission efficiency from the engine to the electric motor, because it's a long path and there is no direct path between engine and the motor and the battery. So a lot of components are coming, their combined efficiency is given by eta TEM. But this charge C, this mode C, PPS charge mode, is very important. You have to understand it from this graph, and you have to understand the difference between capital B and small b. So capital B is partial load, that is graph number line number 4, and small b is on line number 3, which is the optimum operating line. And difference between these two is actually the charging power for the PPS. But if the PPS is charged fully, at the time there is no PMC. Okay, at the time the vehicle or engine will be operating on only B point. So in that case P will be equal to PL. This is what we are going to see next. So in this case you are finding engine alone propelling mode when the demanded propelling power shown as point B is less than the power that the engine can produce. So engine can produce PE, okay, but the vehicle is demanding only B, that is okay. And what you are finding is, in this case SOC of the PPS has reached top line. So previous case C and D, the difference is in C PPS did not reach top line. That means PPS did not reach this height of graph 2. But in this, that's why PPS was getting charged. But in this case the PPS has reached this point 2. In that case engine need not produce this MC. In this case PE will be equal to PL. So when the demanded propelling power shown as point B is less than the power that the engine can produce while operating on its optimum operation line, and the SOC of the PPS has reached this top line. So in this case the engine alone propelling mode is used. So when engine alone propelling mode is used, first answer should be when PPS is maximum or PPS has reached top line. In that case there is no scope that we can charge the PPS more. In this case the D, engine alone propelling mode, is used. Here the electric system is off, that means total motor, battery, motor controller, all those things are totally off. Here the electric system is totally off and engine is only power source for load power demand. That means P is equal to PL. Power output curve of an engine with a parallel load is represented by a dashed line. So you are finding this dashed line. This dashed line appear for the engine when PPS is fully charged. So the engine power, electric power and the battery power can be expressed as P is equal to PL. That means engine power only is equal to load power. PPS is equal to 0. So in this case no charging is happening for the battery. So these were all 4 cases of traction. So I can ask you all these 4 cases for 10 marks. You have to draw the graph. One graph only will do for all the 4 stages, but you have to draw it clearly and you have to explain each of these parts separately and properly. Now let us come to the bottom part of this graph. Bottom part is nothing but the braking power. Okay, so when the vehicle experiences braking and the demanded braking power is less than the maximum regenerative braking power, in that case electrical brake system can be applied. That means you are at point C and this is actually mode E. What is the mode E? Demanded braking power, which is called as a PL. Okay, so this is the load power during braking. So this is PL, which is the braking power now, because vehicle is now trying to reduce its speed, and that speed reduction can be caused only by the PMB. What is PMB? It is given here. It is the motor braking power. So when a vehicle experiences braking and the demanded braking power is less than the maximum regenerative braking power, which is nothing but coming from PPS, electric system can be used only. Electric motor is controlled to a function as a generator to produce its braking power. So in this case, the electrical source, that is the battery only, will produce the PMB, and PMB is nothing but the motor braking power. So braking power will be equal to the demanded braking power. So you are finding in this case the engine is shut down or engine is set idling. That means again you can remove the clutch from the engine to the axle. That means in this case also engine will be idling only, or it can be made shut. Electric power output from the motor and the PPS charging power is, so PMB, that means whatever is the brake power asked by the whatever brake power is generated by the motor, that is equal to PL into eta M. PL is nothing but the demanded brake power multiplied by the overall drivetrain efficiency, that is actually equal to motor power which it has to produce, and PPS is equal to PMB, and finally we are finding PPS is equal to PMB. That means all the braking power required by the vehicle, which is equal to PL, that will be coming from the PPS itself. So there is a easier kind of braking which is called as the regenerative braking, which is produced by the battery only. Last type of mode we are finding that in this case demanded braking power is greater than the maximum regenerative braking power that the electric system can supply. So you see the graph 5. What is graph 5? It is maximum generated power of the electric motor in the reverse direction. So 2 and 5 there is no difference, only 2 is in the forward direction and 5 is in the reverse direction. So if 2 was maximum electric power in the forward direction, 5 is actually maximum power in the reverse direction or brake direction. So whenever the point D, so point D corresponds to mode F. So whenever the actual whatever braking power is demanded by the vehicle, that is greater than 5. So 5 is up to this point. 5 means maximum electrical power can be generated up to this point, but more than that of brake power we are demanding. So in that case electrical braking alone cannot supply the total brake power. So you are finding PL here, this is the demanded power, brake power, and PMB. So PMB is lesser than PL. Who is going to do the extra case? That this extra power is going to be supplied by PMF, written here, and PMF is nothing but the mechanical braking power. So PMF plus PMB together is equal to PL. That means electrical braking plus mechanical braking, they are going to be equal to the overall hybrid braking. So that's why it is called as a hybrid brake mode. So here the electrical motor should be controlled to produce its maximum regenerative braking power. So mechanical brake system handles the remaining portion of the power. That means after PMB, PMF sees how much more I have to generate to satisfy this D. So PMB plus PMF is equal to point D. Motor output power, PPS charging power, and mechanical braking power are given by this formula. So PMB is equal to PMB max because we have already reached 0.5. Then PPS is equal to PMB, so that is equal to PMB max, and PMF is equal to PL minus PPS. Actually you can say that PL is equal to PPS plus PMF. PMF is the mechanical power and PPS is the electrical power. So PL, that is the total load power or total brake power demand, is equal to PMF, that is the mechanical brake power, plus PPS, that is the electrical brake power. So this completes actually all the 6 types of traction, all the 4 types of tractions and 2 types of braking. So all these 6 different cases of a hybrid electric vehicle traction and braking are covered in this 6 modes. So in exam I can ask separately 4 traction modes. So in that case you don't have to draw the graph below, or I can ask only the brake modes. In that case you have to draw only the part below. You don't have to show what is the traction in that case. So this is actually completing all the 6 modes of hybrid parallel electric vehicle operation. Next what we are going to show is we are going to see the flow chart for max SOC of PPS control. So here you are finding the green lines. So these are the 4 modes, A, B, C, D, they are actually traction, and E and F, they are actually called as braking. So now we are going to see whatever we have seen so far, all the 6 modes together. We can explain all those 6 modes by means of this single flow chart. How to do that? Let us see that now. Now let us see the flow chart for maximum SOC of PPS control. In this case what we are going to find is First we are going to see what are the commands from the driver. So what are the traction power commands? That means what is the acceleration, what is the brake, what is the direction command, and then there are command for brake. So acceleration command and brake command, we will compare them in a decision box. Then we will find whether it is traction or it is brake. Question asked is traction. Yes, if the traction answer is yes, then we are going to follow the flowchart towards the downward direction, and if they are saying traction no, that means it is going to go in a brake direction. So right side is the brake, top you are finding there are two brakes, hybrid and regenerative. But let us see the traction case. So whenever it is asking is it traction, answer is yes, that means vehicle will be having the four modes A, B, C, D. How they are appearing one by one, we are going to see through this flowchart. So whenever we know that it is traction, first thing we are going to check whether the speed of the vehicle is less than VEB or greater than VEB. So that VEB is actually called as VER, that is vehicle speed reference. Okay, so this VER is nothing but VEB. So whenever we know that it is in traction, we are going to check whether the vehicle of the speed is less than VEB or greater than VEB. If it is saying that vehicle speed is less than VEB, vehicle speed is less than VEB, that is the question. That means we have not reached VEB yet. That means we are in between that 0 to VEB range. That means this answer is yes. Whenever this answer is yes, we know that if the vehicle speed is not exceeded above VEB, then electric alone traction mode is used. That means only the PPS will give the output to the driving motor, and driving motor will be driving the vehicle, taking power only from the PPS or battery source, because before this VEB, engine is not brought into action. So this is the first decision making stage, vehicle speed, whether it is greater than VEB or less than VEB. If it is less than VEB, then mode A is activated. In this case, mode A is nothing but the electric alone traction system. If the answer is no, answer is no means vehicle speed is greater than VEB. In that case, the hybrid mode can come into picture. Okay, but hybrid mode will come into picture depending on one condition. So whenever we find that vehicle speed is greater than VEB, then the answer is no, then the hybrid mode can come into picture. Hybrid mode means the motor and the engine, they are working together and they are giving out the power together. But for that some conditions are there. The condition in that case is VEOPT. What is VEOPT? It is given here. It is engine power while operating on its optimum operating line. We have found that engine is having two operating lines. One is line 3, another is line 4. Line 3 is maximum optimum operating output from the engine. That is it is going to give the power to the load, as well as it is going to charge the PPS at the same time. So that is actually graph 3, and graph 4 is PPS is fully charged. That means PPS got charged fully from the source 1, then we no need to charge PPS again. In that case, whatever power is generated by the engine, the whole power will be taken to the load power. So in that case, engine itself will be generating less load power. Engine itself will use less throttling action. That means the vehicle controller or engine controller will tell the throttling valve that you get closed little bit, because we don't need to generate more power because PPS is already fully charged. In that case, engine itself will produce less power, and that less power will go to the vehicle alone. So we are here, V less than VEB. Answer is no. That means VEB is more, or vehicle speed is more than VEB. In that case, we have to check whether PTC, TC means traction power, is greater than PE opt. PE opt is the engine power while operating on its optimum operating line. If the answer is yes, that means whatever is the power required by the vehicle, PL, that is greater than engine power, that is very high. So in that case, engine alone cannot supply all the power asked by the vehicle. So PE opt, what is engine power while operating on its optimum operating line, that is line 3. Whether PTC, traction power, is greater than engine maximum power, answer is yes. So in that case, engine has to request the PPS to supply some power as well. So if PTC is greater than P opt, that means engine power is lesser than the demanded power, that case PPS will come into picture and we are going to have a hybrid traction mode, which is called as a mode B. So mode A happens when VEB is greater and the vehicle speed is actually lesser than VEB. Second case, when traction power requested by the vehicle is greater than only engine power, that time engine and PPS together supplies the traction power, which is called as a hybrid traction mode. But if no, that means whatever is the traction power, which this is greater than the traction power is less than the engine power, then you are going to come to the below direction. That means whatever power is demanded from the engine is less than what maximum engine can produce. That means engine alone can supply the traction power. In that case we are going to come below. So if demanded power is less than the maximum engine power, then the sequence is going to come to the lower direction. In this case we have to check whether when the power demanded from engine is low, what is the status of PPS in that case. If the PPS is saturated or PPS is not saturated, so is SOC less than SOC top? SOC top means SOC saturated. So if the SOC is less than SOC top, that means battery is not fully charged, then whatever is the extra power from the engine, that will be directed to the battery charging. So two conditions are there. If PTC is greater than PE opt, answer is no, that means engine can produce higher power than the load power. In that case we have to check whether SOC is less than SOC top or SOC is greater than SOC top. So SOC cannot be greater than SOC top, SOC can be equal to SOC top. So when engine is producing more power, then we have to check SOC status. If SOC is less than SOC top, then send the extra power to the PPS charging mode. And if you are finding that if SOC is almost equal to SOC top, that means there is no requirement to send the power to the SOC. In that case the answer will be no. In that case it will be engine alone traction mode. So for a very good braking performance, the braking forces on the front and rear wheels should be proportional to their normal load on the wheels. This is what they are saying about the wheel itself or the braking itself. Braking power control will not be exactly as regenerative. The control flow chart of the max SOC of PPS is illustrated in the figure. So in that case, first we are starting with the traction part. So traction part, there are four cases. First we have to check whether it is traction or braking. When we convince that yes it is traction, first case whether vehicle speed is less than or greater than VEB. If it is less than VEB, then you have to do electric alone traction mode. If the vehicle speed is greater than VEB, then we have to see whether the demanded power is greater than engine power or less than engine power. If demanded power is greater than engine power, then engine alone cannot supply the power of PL. Then engine has to request the hybrid source, that is the secondary source, battery source, to come and contribute some power for PL. Then the vehicle goes into hybrid mode. If the required power is less than the engine power, then we have to go in only the engine based driving. In that case also there are two cases. First is if SOC is less than SOC top, then extra power generated by the engine will go to the PPS. And if SOC is equal to SOC top, then there is no need to generate any extra power, then only less amount of engine power we generate and we give it to the engine alone. So PPS charging mode is mode C, engine alone mode is mode D. These are the third and fourth mode in traction. Second is hybrid traction mode, when engine power is less than the demanded power. And first mode is electric alone traction mode. So this electric alone traction mode was not there in series. Remaining three modes were there in series hybrid electric drivetrain. Again come back to the initial stage where traction power and braking power, we are comparing them, and if you are finding traction is no means vehicle is not going forward, it is actually going into braking situation, then we have to compare the braking power with the maximum PPS braking power. So PBC, that means required braking power, whether it is greater than maximum brake generated by electrical system or not. If the answer is no, means smaller amount of braking power is requested. So here maximum motor power, that means maximum braking power input is given. We are just checking whether requested brake power by the vehicle is greater than or less than the electrical braking power. If the answer is no, that means electrical braking power is more than the requested braking power, in that case regenerative alone braking mode is sufficient. That was point C, what we have shown in the graph. But if the answer is yes means braking power requested is far greater than the electrical braking power. In that case we have to bring hybrid braking power into picture, and in that case electric and mechanical both together will be supplying the braking. So major objective of this control strategy is when the vehicle speed is higher than the preset value, the engine should be used as the vehicle's primary motor as much as possible. Very important point, that when the vehicle speed is higher than the preset value, that is VEB, engine should be used as the vehicle's primary mover as much as possible. That means case B, C and D, with no pure electric traction. That means we will not be using electric traction as much as possible. So we are talking about actually ABCD, the tractions. Control strategy minimizes the part of engine's energy that cycle through the electric motor and the PPS. So for ABCD, this is the control strategy. This may reduce the engine's energy transmission losses, because we are trying to use engine as much as possible. However, when the PPS is fully charged, that means we are talking about case C. Okay, when the PPS is fully charged, case D, whenever the engine is fully charged, PPS is fully charged and load on vehicle is small, engine is throttled down to meet the small load power. That means we are requesting power is less than the engine power, and SOC is tested. SOC is actually already at SOC top. At that time the engine controller will reduce the performance of the throttling valve. In that case, engine is throttled down to meet the small load power. Here the engine is suffering as operating efficiency becomes low, because we are trying to generate very less power from the engine. Engine is not even there in the mid range of the power generation. So in this case the engine efficiency will reduce. So all the 6 things, that is 4 traction and 2 braking together, we can explain by this flow chart. Okay, so I can ask you this flow chart also for 6 to 8 marks. In that case, all this 6 cases you have to explain with the help of that characteristic graph, where all the A, B, C, D 4 points were shown and many graph lines were shown. So this can be another question asked in the exam. Let us see the last type of characteristics. So one thing we found in the previous, that is max SOC, was in the hybrid mode, engine and SOC, that is PPS, they were acting together. Okay, but in this engine on off thermostat control strategy, you will find never the engine and PPS source both will be in a discharging mode. It will never happen. So in the hybrid mode, in the previous case, in the max SOC, both engine and PPS were in discharging mode. But in this case, engine on off thermostat control strategy, where on off of the engine is done by the thermostat based controller. In this case, you will find that initially when the engine is on, actually which is made on by the thermostat. Why engine is made on? Because PPS charge storage is 70% only. That means PPS is at the discharge threshold, discharge lower threshold. In that case, we find the need to charge the PPS. That's why engine is turned on, okay, by the thermostat based controller. And then engine is on means it will be giving the load torque, as well as it will be generating power which will be charging the PPS, that is the source 2. And you are finding that PPS is charging here. At the same time, engine is running the vehicle. How long will it happen? It will happen till the battery or PPS source reaches 100%. As soon as the PPS source reaches 100%, the thermostat will do what? It will turn off the engine and it will turn on the PPS source in a discharge mode. So as soon as the PPS source is going up to 100% or fully charged, SOC 100%, in that case engine will be turned off. So engine will be idling in that case, and in that case the PPS discharge mode will be on, and PPS will be driving the whole vehicle in that case. How long? Okay, so only in this part, as long as the engine is off, PPS will be driving the whole vehicle, and the PPS will start getting discharged. So in this case, engine is off, PPS is in discharge mode. What happened in the first case? First case, engine was on. This was giving the power or load power to the vehicle, as well as this was charging the PPS source at the same time. But in the second case, when the engine is off, at the time no charging of anything happens. In that case, PPS goes into discharge mode, and PPS gets discharged up to 70%. Whenever the lower threshold is touched, immediately the thermostat, it turns on the engine. Again engine supplies the load as well as engine starts charging the PPS source. So you are finding that PPS is again charging, but every time PPS charging characteristic you are finding it is different. Okay, so there are 3 charging and 3 discharging profiles of PPS is shown. All these 3 profiles are different because they are depending on vehicle braking condition, road condition, traffic condition, everything. So never you will be finding that the charging and discharging graphs of PPS is similar. Okay, but the characteristic of the engine on off and the PPS on off charging discharging remains same. It will start charging from 70%, it will go up to 100%. As soon as 100% of the PPS charge is reached, the thermostat actually switches the engine off and it turns the PPS on. Again the PPS starts discharging through the vehicle load, and again it comes to this point where the engine is started again and PPS starts charging. So when a vehicle operates in a state in which the load power is less than the power that the engine produces at optimal operating efficiency and the PPS is fully charged. Okay, so here PPS is fully charged. Max SOC PPS control strategy forces the engine to operate away from its optimal operating region. That means in the previous case whatever we have found, that engine wants to operate, engine wants to charge the PPS as well as give the maximum output to the vehicle. But if the SOC is fully charged, in this case engine actually don't get to work in its optimum operating region. So in that case engine alone traction mode, in engine alone traction mode actually engine efficiency is getting less. That means engine is losing its performance. To solve this problem, the next characteristic or next type of control strategy, that is engine on off control strategy, is devised. So whatever we found in D, engine alone traction mode, in this case engine is operating away from its maximum operating efficiency region. To counter this engine on off thermostat control strategy is used. In this case the overall efficiency of the vehicle suffers. That means if it was D, in that case overall efficiency of the vehicle suffers. On this situation the engine on off thermostat control strategy may be used. That means up to C it was okay, A, B, C it was okay, and as soon as the C thing is done, that means PPS is fully charged, then don't use D. Okay, then use the PPS to run the vehicle instead of engine working with lesser efficiency. So up to C max SOC is correct. Just after C try to apply this engine on off control strategy. So consequently overall efficiency of the vehicle suffers because of D operation of the vehicle. So in this situation the engine on off control strategy may be used. Here the operation of the engine is controlled by SOC of the PPS as shown in the figure. During the engine's on period, control strategy is max SOC of the PPS. Here the engine is always operated in optimal curve. That means there is no fourth curve in the engine at this operation. Whatever fourth curve we have found, graph number 4, that will not happen in this case. Either engine will operate in optimal condition or it will be shut off. So when the SOC of the PPS reaches its top line, at that time the engine is turned off and the vehicle is propelled only by the electric motor. So as soon as the engine is turned off, the battery takes the charge and the electric motor will be running the whole vehicle. When the SOC of the PPS reaches its bottom, that means this point, the engine is turned on and engine will be working with its maximum efficiency, engine will be working with its optimum efficiency, and the engine will be doing two things. It will be running the vehicle, it will be charging the SOC of the PPS. This control strategy uses the electric motor as the primary power source. Not every time, not in the first case when engine is on, but in the second case yes, whenever the engine is off, at that time the electric motor will be acting as a primary power source. Engine either operates in optimal region, that means in the first case, in this region, whenever engine is operating, it will be either acting as in the optimal region, or in the second case it will not be working at all. So in this strategy, thermostat control strategy, the engine will never operate in suboptimal region. This you have to understand. Okay, in the previous strategy max SOC, in engine was operating in optimal condition, that is graph 3. Engine was operating in suboptimal condition, graph 4. But in this engine on off thermostat control, engine will never operate in suboptimal condition. However, contrary to this max SOC PPS control, the engine energy that goes through the electric motor and PPS is also maximized. When is engine charging this uh, max SOC and PPS. Okay, because when the engine is totally on, it is working in the optimal region, it is driving the load, and whatever is the remaining energy, maximum energy produced by the engine, that will go for charging the electric motor and PPS. Hence, engine energy that goes to the electric motor and PPS is also maximum. It may cause more energy losses in energy conversion. With this control strategy, electric motor must have sufficient power to meet the vehicle's peak power during the engines at all period. So you have to prepare actually both these questions, that is what is max on off control. There are ABCD 4 traction stages or modes, EF to brake stages, and the D part of that max SOC PPS, it was actually reducing the overall efficiency of the engine. So to counter that, this engine on off thermostat control strategy is invented, and if used properly, if the algorithm is designed properly, together that max on off and max SOC PPS and on off thermostat together, they can give the best control strategy for parallel hybrid electric drivetrain. So this controls this lecture. Here we are going to have some 1 or maximum 2 lectures after this, and that will be the end of this module and the syllabus. Thank you.